Hi everybody. So today's lesson is about mass defect and nuclear binding energy. So in the last lesson we learned about nuclear stability and we looked at what are the forces that act within the nucleus of any atom. So there's two opposing forces. So there is the strong nuclear force that holds the neutrons and the protons together in the nucleus, but there's also the electrostatic force of repulsion. Okay, so we know that. Now, when scientists look at the components of a nucleus, let's take the helium nucleus for example, which is the same as an alpha particle. The helium nucleus consists of 2 protons and 2 neutrons. So helium has 2 protons and 2 neutrons. So if you measure the individual masses of 2 protons and 2 neutrons, in theory, these 2 masses should add up to the measured mass of the helium nucleus. But it is found that they were not the same. They found that the sum of the masses of the 2 protons and 2 neutrons is slightly higher than the mass of the helium nucleus itself. Now this difference is what's called mass defect. And for a long time, scientists were wondering, why is that different? Because haven't you always learned that mass is accounted for? Like even though there's some sort of a reaction, the total mass at the start should be equal to the total mass in the end. But this didn't seem to make sense with nuclear reactions. So that's when Einstein came up with his theory. So till now, we thought that matter is made up of mass and just mass. However, what Einstein said was matter is made up not only of mass, matter consists of mass and energy, and these two are interchangeable. So when you bring protons and neutrons together in order to form the nucleus of an atom, these protons and neutrons actually lose some of the energy to be bound in the nucleus of the atom. So it's almost like me taking this string. So you've got the free protons and neutrons. So imagine my fingers are the free particles and they're allowed, so they've got lots of mass, lots of energy. But if I need to bind it, bring them together to bind it, to form the nucleus of the atom, these protons and neutrons, they can hardly wiggle. They don't have much energy, and the more tighter I bind them, the less the energy they have. Now, where's this extra energy? Where's that energy that's taken away? How has it appeared in the nucleons of the nucleus? Is that the energy that has been removed from them to bring them together, to bind them tightly, has actually resulted in a loss in mass. So whatever mass is lost because of the nucleons coming together has actually been removed as energy. So if you need to free the nucleons, you've got to give it energy. And the energy that you give it is what we call binding energy. So this binding energy, you give it energy and it becomes free. So when you give it energy, what difference are you going to see is that the free protons and neutrons in their free state also have more mass. So they have more mass and more energy. So one of the questions that we do is just looking at how do you calculate this is the mass of a proton. So I'm taking the data from this page here. So hydrogen consists of 2 protons and helium consists of 2 protons and neutrons. So the mass of 2 protons and 2 neutrons is 2 times 1.67338 plus 2 times 1.67438, and you multiply that by 10 to the power of negative 27 kilograms. Don't forget that one. Okay, so when you do that, you end up with, this works out to 6.69552 times 10 to the power of negative 27 kilograms. When you do that, you end up with this answer. Then if you look at this table again, and you look at the measured mass of an alpha particle, so that's over here. So the measured mass of your alpha particle, which is the helium nucleus, is a bit different. It is 6.64591 times 10 to the power of negative 27. Can you see these two numbers are a bit different? So when you subtract the two, what you get is called mass defect. So mass defect, the symbol is delta N, and the difference between the two is 0.04961 times 10 to the power of negative 27 kilograms. Okay, and then so to find out what the energy is, the binding energy, so the binding energy is given by Einstein's equation, which is mass defect times the square of the speed of light. So the binding energy is 0.04961 times 10 to the power of negative 27 times square of the speed of light. And then when you do that, you come up with a really small number, which is 4.4649 times 10 to the power, let's write that properly, negative 12 joules. Okay? Now, the thing is, every atom with the nucleus, they have several nucleons in it, and the stability of a nucleus depends not so much on the total binding energy, but actually the stability of a nucleus depends on the binding energy per nucleon. Okay, and so the greater this binding energy per nucleon, the more stable the atom. I'm just going to rub out the top part. I still need this number because I'm going to show you something in a bit. So what you need to be familiar with is the binding energy curve. So you have on the y-axis, you have binding energy per nucleon. And on the x-axis, you have the mass number or the nucleon number. Now, the shape of this binding energy curve, so actually ordinary hydrogen, which has only one proton in the nucleus, doesn't have any binding energy, so it doesn't need to be bound to anything else in the nucleus. However, isotopes of hydrogen, deuterium, tritium, will have some binding energy because the isotopes of hydrogen have neutrons in the nucleus. So the binding energy curve looks something like this. There's some peaks, and then it goes up, and it comes down like this. Okay, so what you see here is probably your deuterium and tritium hydrogens there with no binding energy. This peak here is helium, this peak here is oxygen, and so on. But at the top here is iron. And then, can you see, so iron has at the top of the curve, it says, so that means that the nucleons of iron have the highest binding energy. The implication is you need to give the nucleons of iron the most energy in order to set them free. Okay, so that's what this represents. Anything beyond iron will have less binding energy. Okay, and there's also another graph that also explains, and this is looking at the mass. So things with more binding energy, the nucleons themselves have less energy because you need to give them more energy to set them free. Okay, there's also the mass per nucleon against mass number. So this is mass per nucleon and mass number. So this graph is nucleons with less binding energy will have more energy themselves and also greater mass. So this curve looks something like that. Okay, and the bottom of the curve here with the lowest mass is iron. So the nucleons of iron have the least energy, okay, and they also have the least mass. Okay, so when they lose energy, they also lose mass. That's the whole thing about this. And the other thing is, can you see this number? The binding energy per nucleon is like something times 10 to the power of negative 12 joules, which is really a very, very small number. So there is also another way to express binding energy and that is in terms of electron volts. So the electron volt is defined as the amount of kinetic energy an electron gains when it's accelerated with a potential difference of 1 volt. So if you've got two oppositely charged plates, positive and negative, and there's an electron, when the electron's free to move, it's going to accelerate towards the positive plate, and if the potential difference is 1 volt, if it accelerates, it's going to gain kinetic energy. So that's the electron volt. And in order to convert this to electron volts, all that you do is divide this number, which is in joules, divided by the charge on an electron, which is 1.6 times 10 to the power of negative 19 coulomb. So you end up with a slightly bigger number. In terms of electron volts, you get 6.976 times 10 to the power of 6 electron volts. So that is this lesson, lesson 2, and I hope that helped, and you can watch this when you have time to just go over concepts. So bye for now, and hope your day goes well.